3, 4. For example, my 10, right? If I want to add vector A and a vector B, so it's actually you add 3 plus 7, right? And then you add 0 plus 8, and you add 4 plus 10. So this one is engineering notations, as I mentioned to you, if I use engineering notations, automatically you know that this is x-axis, this is represented by y-axis, and this is represented by z-axis, right? So what we call here x, y, z is the coordinate system, right? This is what we call by the coordinate system, uh, which you use XYZ to represent, and this is Cartesian coordinate, right? This is Cartesian coordinate. The most common coordinate system that we use in this course, right? But of course, beside the Cartesian coordinate, you will also encounter some of the coordinate system, the alternate coordinate system, which what we call by cylindrical coordinate system, right? And also you may also encounter another coordinate system, which what we call by spherical coordinate system. Okay, so those are the coordinate system that we will use from time to time to solve the problems in electromagnetic, right? So this is the vector algebra. This is how you perform uh, the operations, the additional operations of the vector, right? Beside that, also subtractions also the same, right? So you only perform according to the axis of the vector. Okay, that are the things that uh, which we consider as a fundamental of this and also the subtractions. But when we comes to the um, multiplications, so when we talk a little bit about multiplications, there are two things, there are two ways to multiply in a vector, right? There are two ways to multiply the vector. We can use a dot multiplications, right? This is what we call as a dot product. And also we can use a cross product, right? This is the dot and cross product of the multiplications. Okay, so before we go further into the multiplications, in the vector is usually divided into two types of the vector. One is what we call as the positions vector. Another one is what we call as the distance vector, right? So what we mean by the positions vector, which means, for example, if I have a coordinate systems, right? X, Y, and Z, right? And I have a vector. I have a vector from the what we call the center of here. It's what we call this. I totally forget what we call the terms 0, 0, 0. Can anyone help me to recall?
Origin.
Origins. All right. Okay. I'm too old to recall this. This is the origins. All right. Origins means 0, 0, 0. Okay. So if I have a vector A, for example, right? This is my vector A. My vector is start from the origins, right? This is what we call as a positions vector, right? This is what we call as the positions vector. Beside the positions vector, we also have the distance vector. What we mean by the distance vector, in this case means I have a vector which not start from the origins. For example, I have a vector like this, which is floating in the space of 3D, right? So this is my vector B, right? This is my vector B. And then we call this vector as S1, as a distance vector. And we also know that the distance vector, for example, if I have uh, a starting point and end point, so if I have A and B over here, right? So my vector B is actually a vector from A to B, right? This is my vector B, right? Sorry, the small letter, um, this one I should write from A to B with the arrow, okay? Right. But in order to have to identify my vector B, is the distance vector is actually rely on the uh, positions vector. How do we say the things rely on the positions vector? Because from the origins to should show it a straight line. The A point, right? This is what we call as a positions vector. And we can have another positions vector which from the origins to the point B, right? If I label this as vector A and I label this as vector B, small letter, right? And in order to identify vector capital B, I can use my vector B minus with vector A. This is the positions vector, right? This is the positions vector. The small letter A also a positions vector. If my vector is opposite directions from B to A, then I can label this from B to A. So I can eventually find out my vector is from uh, so from A minus B, right? From A minus B. Okay, right? So that is the two things which is highly related to um, the vector positions and the vector um, distance. Okay, so so we have done on the vector, but before we go further, let's take a look on the multiplications, yeah? On the vector multiplications. Okay, so on the vector multiplications. So as I mentioned just now, we have a dot product. We have a dot product, and we have a cross product. Right. This is two vector multiplications. And what we produce when the dot product will produce a scalar quantity. Right. The dot product produce the scalar quantity, and the cross product produce the vector quantity. Right. So these are the two things. And when we perform the dot product and the cross product, among two vector, for example, for dot product, um, dot product. So if I have a vector A, if I have a vector B, right, this is vector A, this is my vector B, and I have a small angle between here. This is what we call as theta. Okay, so when I perform vector A multiplications with vector B dot product, what we have is actually the magnitude multiplications of the magnitude of both, and also you will have cos theta AB, right? This theta we refer to the small acute angle on the here, because there is another angle what we call here. There is another angle over here, which is obtuse angle, right? But this formula refer to the acute angle, which is a small angle compared to the larger angle, right? This is what we call as a small angle. So the theta is the differences between the two angles. So if there is no differences, then your theta will be equals to 0. Okay, so that is the dot product. Okay, what else? For the cross product, um, okay, for the cross product, let me see. So this is a little bit tricky, but okay, uh, let's talk a little bit more on the unit vector. What about the unit vector when you dot product, right? So the unit vector, remember this, for the dot product, unit vector x, which is on the x-axis, when you dot with another axis unit vector, you will always have 0, right? This is the dot product. And is also equals to ay dot az is also equals to az dot ax, right? Everything will be 0 if you dot product with different types of the axis. Okay, but if you dot product with the same type of the axis, for example, ax dot ax, it will be equals to 1. Ay dot ay will be equals to 1. Az dot az will be equals to 1, right? So this is the unit vector multiplications for the dot product. Okay, then what about cross product? What about the cross product? Let's move to the page. Okay, so vector multiplications. On the cross product. So this one will be a little bit tedious. The way we extract the informations of the cross product will be a little bit tedious, right? If you still remember, A cross B, right? How do we perform A cross B? For example, to perform A cross B, we usually use matrix multiplications. If you still remember, AX, AY, and AZ, right? And then what you need to write over here is A component magnitude of A, magnitude of Y, magnitude of Z for vector A. While on the other side, magnitude of B vector, magnitude of B at Y, and magnitude of B at Z, right? Because we use A, we represent A with AX, AY, and AZ. This is in engineering notations. And we know that the directions will be AX, AY, and AZ, right? But we never write out the directions because this is engineering notations. So if you want to write out, you need to spell it out on the full notations, right? So for this one is also the same, BX, BY, and BZ. Okay, so in order to multiply, we will need to identify what is inside the what is actually inside the bracket. But what we want to find is fixed AX, all right? And then minus with what is inside the bracket AY, and plus with what is inside the bracket AZ. This is fixed, right? All the time. If you still remember how to perform the vector multiplications by using the cross product if during your uh, engineering maths 1, right? This is what we need to fill in. AX minus is fixed. AY plus AZ, right? And the things inside here depends on how it's available. For example, I shows one example on AX. Yeah, if I want to find AX component over here, I will. This is my AX. All right. You cross all not related to row and column. What you have over here is this one, right? And what you need to do with this one, you cross multiply, right? You cross multiply and minus. So AY multiply with BZ minus with AZ multiply with B1, right? This is how you obtain the element, the, the magnitude element in the cross multiplications. So you repeat the same things for AY and AZ, right? Okay, so this is one way you can identify the directions and the magnitude. Okay, and then beside this, if you still remember, I introduced cyclic permutations, right? Permutations. So the cyclic permutations is actually also a way, a fastest way to obtain the cross multiplications. What we means by the cyclic permutations over here, you can use I don't want to draw the figure, but let me extract it from the textbook. The cyclic permutations should be at the page. I remember this one. Yeah, this one. Okay. So let me extract this. Okay. Okay, so, so this is the figure of the cyclic permutations, right? So if you notice over here, there is a clockwise and counterclockwise. So over here, this is clockwise. And over here is counterclockwise. What we have over here, for example, AX cross with AY. AX cross multiply with AY. What you have, the directions will be AZ, right? The directions will be AZ. So same as well for AY cross with AZ, the directions will be AX. And the same things, AZ cross with AX, the directions will be A1, right? So this is one way to obtain the unit vector for the cross multiplications. Right? The unit vector for the cross multiplications, right? So in the dot product, I shows you the unit vector will be always uh, if the dot product with the difference axis, you always get 0. If you dot product with the same axis, ax dot ax, you get 1. Ay dot ay, you get 1. So that's why when you perform the dot product, automatically you cancel out the unit vector, right? You cancel out the informations of the directions because the informations of the directions will be equals to 1 if the same axis unit vector is a dot product together. But the things difference when you come on the cross product, right? So the unit vector can be identified by using these cyclic permutations, right? Or you can use this one, the complete cross product multiplications. Okay, so this is um, the, the things that I want to show on the vector, part of the vector, right? As the revisions. Okay. Up to now, do you have any questions regarding the vector revisions? You have any questions? Boleh
Now tak ada.
okay, open up the mic kalau ada soalan. Jangan risau.
Saya ada.
Right? Okay, so that is one part on the vector. What we need to do next? Yep. Belum ada lagi Alright. Okay, so kalau tak ada, we move to the electrostatic. The first part of the electrostatic. Okay. Electrostatic, right? So this is on chapter 4, right? This is on chapter 4 of the textbook, chapter 4 of the textbook. Actually, in our syllabus, this will be the chapter 1, or maybe chapter 2, because the first chapter is actually the basic um, mathematical review. The second chapter will focus on the electrostatic part. Okay. So what we have on the electrostatic, hold on for a while. Okay, so in electrostatic, we start with a charge. We have positive charge, we have negative charge, right? The interactions between the charge will be from positive to negative, right? The charge will move from positive to negative. There is electric field that which will be generated. This is what we concern. This is what we concern. Because we are electrical engineer, we are electronics engineer. What we concern is on the electrical field, which is generated by the charge, right? And the charge we represent with Q, the capital Q, right? And in order to obtain electrical field, we always start with Coulomb's law. What we means by the Coulomb's law means if you have two charge, for example, no matter the charge is positive charge or negative charge, as long as I have the two charge and the distance in between the charge, for example, this is R, right? And it will generate because the charge itself will generate a force, right? So when you have the two charge itself, the force generated at Q1, you will feel the force that generated by Q2. At Q2, you will feel the force generated by Q1. So the force from Q1 2 and the force from Q2 1 will be generated, right? And this is what we call as the Coulomb's law. And in order to identify how much the force, right? How much the force, for example, we will actually, using the Coulomb's law, Q1, Q2, which is the magnitude in between the two force, divided by 4 pi epsilon naught r squared. All right. And then we don't forget about the unit vector, the directions of the vector. So what is actually epsilon? Epsilon is permittivity. Permittivity of free space. Right? Epsilon is permittivity of free space. Is a constant. Is a constant. You can use either 10 power of negative 9 divided by 36 pi, and or you can use 8.854 times 10 power of negative 12. The unit will be farad per meter. Now, my warning to you, if you cannot remember epsilon naught, definitely you will get 0 for the for all the calculations that you face, right? Don't tell me you cannot remember epsilon naught. Don't tell me you cannot remember epsilon naught after 14 weeks of the class, the constant, right? Don't repeat the same mistake in test 2. What is epsilon naught? What is mu naught? Those are the things that not supposed to be happen, right? Okay. So this is the Coulomb's law. The Coulomb's law that we use to identify the force in between the charge. Okay. Then from the force provided, what you will get, because as I mentioned, I only care about the electric field intensity. And electric field intensity is actually related and have a relations with these definitions, with the force. When you divide the force with the charge, this is what we call as the electric field intensity. Electric field intensity, the unit will be voltage per meter. All right. Or you can say electric field intensity is the force per unit charge. Because beside voltage per meter, we can also use, because the force is Newton per coulombs. Either one is correct. But the normal one, we always use voltage per meter, right? This is the relations in between the force and the electric field intensity. Okay? Boleh guys?
Boleh.
Bisa.
Nah, okay. Right. Okay. Then from E field intensity, we move from 2-point charge, or if you have 3-point charge, for example, if you have 3-point charge over here, right? This is my test charge, for example. This is my Q1, this is my Q2, this is my Q3. So if I want to know how much force created by Q1 and Q2, for example, right? So the Q1 will create a force to Q3, and the Q2 will also create a force to Q3, right? So if you calculate, you can easily calculate the force in between Q2 and Q3, right? 4 pi epsilon naught r square AR 23 plus with Q1, Q3 divided by 4 pi epsilon naught R2 AR 31. Okay, that is the way to calculate the total force generated by the two charge, and we call these as the superpositions, right? Superpositions. The theorem of the superpositions, which means you overlap all the, you sum all the force created. Okay, then what else that we need to know? Continuous charge. All right. Continuous charge consists, this just now I introduced you on the point charge, that after the point charge, if I have 1-point charge over here, right? If I have another point charge over here, another point charge over here, another point charge over here, then if I add up all together, it will become a continuous charge. And if I do it in the one line, we call this as the line charge. Yeah, we call this as the line charge. Okay. Then if I arrange my point charge in an area, so which means I have all the charge which arranged properly, few line charge that arranged properly, right? So it will become something like this, right? It became something like this. And we call this as the surface charge, right? We call this as the surface charge. Or if I put it in the way, in a volume, I put it all the point charge in a volume, right? 1 meter over here, 1 meter over here, and 1 meter over here. So if I want to find the volume, I multiply 1 meter by 1 meter by 1 meter, it will becomes 1 meter cube. If I have, for example, this 1 meter, my length also 1 meter over here, my surface area, if I multiply, it will becomes 1 meter square, right? So if I measure the length of this line, it will becomes 1 meter, for example, right? For example. Okay, then why do we use this 1 meter? Because this is actually the standard unit to deal with the continuous charge. Why? Because if I have the line charge, for example, you have the line charge which is longer than 1 meter, no matter how long is that, and you assume the line charge, the charge is distribute evenly, right? You assume the charge distribute evenly, no matter how long is that, you only need to know 1 meter, how much charge inside 1 meter. And we call this as rho L. And this is line charge density. This is line charge density, right? How dense in 1 meter? And the unit will be how many coulombs in 1 meter, which means coulombs per meter, right? This is line charge density. When you see rho L, this is line charge density. Then the same things happen. I want to know how much charge in one big surface. You don't care how much charge in one big surface. You only take 1 meter by 1 meter over here and you count how many coulombs inside, how many charge inside. And we call this as rho S. We call this as rho S. And this rho S is called as surface charge density, right? And the unit is coulombs per meter square because you count how many coulombs in 1 meter square. The same things happen for the volume charge. The same things happen for the volume charge. You only care how many coulombs in 1 meter by 1 meter by 1 meter cube, right? So you count how many charge inside per meter cube. And we call this as rho V. And this rho V is volume charge density, right? Without these three parameters, you cannot calculate the total charge in one area or one length or in one volume, right? This is what we need to use. Okay, so usually how do we use that? How do you use that to calculate the total charge? Because we concern on the total charge, right? For example, I have a length over here. For example, the length is 10 meter. And I know that in 1 meter, right, in 1 meter, there is, let's say, 20 coulombs in a cable length. Then automatically I know my rho L will be equals to 20 coulombs per meter. This is my rho L. In order to calculate the total charge available on that one particular length, my charge can be used with rho L dl, right? Integrate, because you need to integrate each of them. Integrate means you sum every single things with respect to rho L and dl, right? So when you integrate rho L dl, automatically you obtain the total charge. Okay, so for example, I have my rho L 20 coulombs per meter. Multiply with my L over here is 10 meter, right? So automatically you know that 20 multiplied with 10, you have 200 coulombs, because your M over here is automatically cancelled out. So this is how you actually identify the total charge in one length. The same things happen for the surface, the same things happen for the volume. All right? Boleh?
Boleh.
Okay. Apa lagi? Okay. Okay, let's take a look on the formula, right? Being given to you the formula. This is the examinations formula which being introduced to you during the test 1 and test 2, and we will give the same things to final exam, right? So you can see over here, there is a mathematical formula over here with differential length dl. So we have a different coordinate system. The coordinate system for x, y, z, Cartesian coordinate, cylindrical coordinate, and spherical coordinate. All right. So before we go into here, maybe I need to introduce a little bit on the coordinate system. Yeah, hold on, yeah. Let me move to another page. We introduce a little bit on the coordinate system. Right? Please be patient before we go into some example. I need to revise all of the basic things before you can clearly identify them. All right. The coordinate systems, what we have over here, supposed to be in the first chapter, but let me show you here. Okay, so you see this, the Cartesian coordinate, right? The Cartesian coordinate. So in Cartesian coordinate, we have three parameters, x, y, and z over here. So the limitations on each of the Cartesian coordinate axes, x-axis, y-axis, and z-axis over here, is zoom in. So you can see x, y, and z. There is no limit. The limitations is goes from negative infinity to the infinity, right? Same as another others exist, right? So these are the three parameters that used to represent the coordinate systems for the Cartesian, or sometimes we call this as rectangular. Okay, all right. Then there is another types of the coordinate systems, what we call as circular or cylindrical coordinate systems. And in these coordinate systems, we use these three things, three parameters, rho, phi, and z. And how we represent these three parameters? Take a look on this one, right? So this is the cylindrical coordinate. Rho is actually the radius, right? This is rho. So imagine that you have one cylinder. So how big is the cylinder? The round shape, the circle shape is determined by the radius. And this radius, we use rho to represent, all right? Another one is how tall of your cylinder, and how you decide how tall is represented by z, right? The z-axis. And another one is how complete is your cylinder. So for example, in this case, in this image, you don't get the complete cylinder. You go, we don't get the complete circular shape of the cylinder because the theta decide the completeness of the cylinder, right? So each of them are having the limitations. And what is the limitations? Limitations comes from this one. Your rho can only start from 0 to infinity. You cannot have your radius with negative, right? So definitely your limit, the limitations of the parameters should start from 0 up to the infinity large. Next is the phi. If you have the complete circular shape, you have 2 pi, which is equivalent to 360 degree, right? So this is in radius. The radian, you put it in 2 pi, 0 to 2 pi. And how tall of your cylinder, the limitations have as no limit. You can go from negative infinity up to the positive infinity, right? There's no limitations on that. So you use this to represent cylindrical, right? You use this to represent cylindrical shape. And the last one is what we call as spherical, right? We use also three parameters to describe the spherical shape, because sometimes your object is in spherical and you put it and you represent the object in spherical coordinate system. So we also use three parameters, radius, theta, and phi. So what is this spherical? If you have a complete spherical like a ball, then you will have different limits of the parameters. All right. For example, how big is your ball is represented by the radius of the ball. Is in this case a spherical coordinate system, we use r, right? Small letter r. How complete is your ball is represented by phi. And there is another one, which is the theta, which the reference is comes from the z-axis. So each of them are having the limitations, also on each of the parameters. And what is the parameters limitations? From here, I shows you the limitations will have the radius from 0 to infinity, the theta from 0 to pi, and the phi is from 0 to 2 pi, right? So these three things will determine the completeness of your shape in spherical. Okay, so that is the coordinate system which I would like to review. Now, when we talk about the coordinate system, we need to touch a little bit on the vector calculus. Vector calculus, let me show a little bit of the vector calculus which related to this one. One. Okay, let's take a look on here. The vector calculus. Okay, for the vector calculus, when we talk about the Cartesian coordinate system, right, look at here. The Cartesian coordinate system, as I told you, we have x, y, and z. So if you take a look on here, look at this picture. So each of them is represented by a small differences of the y, small differences of the x, and small differences of the z. So if something change, the y axis change, you have dy. If z axis change, you have dz. If y x axis change, you have dx. Right? So the changes of the length itself can be represented with this dl, for example, right? dl is the changes of the length. In which part they change represented by x-axis, y-axis, and z-axis. It can be changed at the x-axis. We use this one, dx. How much it change? How much the magnitude of the changes? Dx, maybe they change 5 meters. So that is the changes. They change 5 meters towards positive. Then you have positive dx. If they change 5 meters towards the negative x-axis, then you will have negative dx, right? So this is how you identify the changes. So in general, for Cartesian coordinate, you know that only dx, dl you need to know, or you don't have to memorize. In fact, from the formula itself, you can see from here, the first page of the formula, you can see the Cartesian coordinate. Your dl is dx, ax, dy, ay, dz, az, right? Then what about cylinder and spherical? All is the same, but they have different parameters. So if I shows you the parameters of cylindrical coordinate, this will be this one, right? You have dl, the changes of the length can involve the changes of the radius towards the directions of the radius, or the changes of the phi. But when you change the length of the phi, you must include rho, the radius, together. or you have changes of the type of the cylinder, you have DZ, right? So this one you don't have to memorize. This one is actually available over here as well. Same as well for the spherical. So all the DL is available, and also DS also you don't have to memorize. You have the surface and you have the volume, depending on which coordinate systems you want to use. All right. So if you forgot this, just refer back to the formula sheet, right? You don't have to memorize. Okay. And for the electrostatic, as I mentioned just now, um, if you have the if you want to find the charge dl, ds, and also you can find dv. So this is how you multiply and integrate rho v dv, rho sds, and rho ldl, right? And then if you look at this is the formula for the Coulomb's law, which I just shows you just now, and how you relate the Coulomb's law to the E field intensity is by dividing the charge with respect to the force. All right. So these are all the things that I introduce to you. Uh, okay. Beside we just now we start from right. We start from the charge which produce a force, and then I introduce when your charge divided by the force divided by the charge, then you produce the E field intensity, right? And also, I would like to introduce another one, which is capital D. So what we call as capital D is the flux density, right? The flux density. And the flux density can be related with the E. They have some relationship between flux density and also the E field intensity. But before we move there, let's do some example which related to this. Let's which type of example I should try it out. Okay, maybe we can try one example over here. Square plate. That maybe shows. Okay, so we'll try one example. Um, Example one. Straight away we move to the surface charge because line charge will be much more easier for you. So let's take a look on the surface charge, one example, and another example with the volume charge. Right, so you have a square plate in the Cartesian coordinate, right? For example, um, let's draw a square plate over here. A square plate. And is the square plate is actually located, this is x-axis, this is y-axis, this is the z-axis. So the square plate is actually located on the floor, right? For example, so this is all the surface of the square, right? The length is actually over here. This is -3, and this one is 3. And also for the y-axis is also -3 and 3. Right. So the square is actually located on the floor, and they have the surface charge density rho s equals to 2y square with microcoulombs per meter square. Right. These are the things that are given to you. A square plate in xy plane is situated in the space defined by -3 meter in between x. So if I write it out, over here, -3 meter x and 3 meter, and also y, -3 meter, and this one 3 meter. The questions ask you to find total charge on the plate. On the plate. So if they give the surface charge density, this is the surface charge density. Surface charge density given with 2y squared microcoulombs per meter, right? So how you want to solve this? How you want to solve this from the one that we learned before? So if we look at the formula, look at the formula first. Now, this is the problems with the surface, right? Why I say is the problem with the surface? The first thing I said, because the rho is rho s. They give a plate on the floor, and that is the surface charge density. They give you the surface charge density. Then you know automatically this is rho s, and this is the surface charge. And then you know that the problem is actually located on the Cartesian coordinate, which is x, y, z. Okay. So if I look at the formula given to you, you know this is the problems with rho s. This one. Because I want to find Q. I want to find Q, which is here. And why I choose rho s ds? Because it's given in the questions. I don't choose rho L. I don't choose rho L. I also don't choose rho V, right? I don't choose this one. I don't choose rho V because it's not related to the problems. So I choose this one. Okay. So now Q equals to rho S ds. So I can start with this one. Q equals to integrations of rho S ds. Now, in this case, since is the surface can change. The ds is the changes of the surface. Why will change this? What is the changes will be made by the Cartesian coordinate when the surface change? Of course, your x-axis change, your y-axis change, right? This is the surface changes. So when your x-axis change, your y-axis change, the length of the x and y change, the surface area change, right? So in this case, we can say our ds is actually dx dy, right? Our dx dy. So if I put it over here, I integrate, right? I integrate.
Doktor,
Yeah,
nak
yes.
tanya yang
Okay.
boleh ulang yang ds equal to dx dy itu kenapa?
Okay. Okay, let's take a look on this one. Okay, tengok dekat sini formula yang saya bagi dekat sini, Cartesian. So, cuba bayangkan kita ada satu surface. Surface yang macam mana cakap ni? Kejap, saya tunjuk ni. Sebab dalam Cartesian coordinate, you akan ada surface, right? Akan ada surface. So all the surface, it can be dx, dy, or you can be the surface on dz, dz and also maybe dy, right? Kejap sekejap. Okay, so you can be on the Cartesian coordinate, you can boleh have the surface of dz maybe on dx. Also, maybe you can, maybe this one is dy. Okay, so you may also have the surface in between this one, maybe in between dz and dx, right? All the three types of the changes will have the changes of the surface. But since this one, in the problems, the surface is actually located on x and y. So imagine your x change and your y change, definitely your surface area will change, right? So that's why we have our ds equals to dx dy. Is that okay? Boleh.
Boleh.
Okay, so since you know that your ds is equals to dx dy, and you also know that your rho s is 2y square. 2y square. My ds is dx dy, right? And if we integrate, if you look at this dx and dy, means you have double integrations, right? You have double integrations. Why double integrations? Because you want to integrate the changes on dx. At the same time, you want to integrate the changes of dy, right? You have the double integrations. And of course, don't forget about the unit. The unit for rho rho S just now is microcoulombs per meter square, right? This is the unit, microcoulombs per meter square. And if you multiply with the DS unit over here is meter square because it's the area, right? Meter square. Okay, so this one is meter square, I think. Yeah, the meter square and meter square. So automatically your meter square will cancel out, right? Then you will only have the coulombs, which is the charge, the unit of the charge. Okay, so now when I integrate, you can integrate with respect to you can let me solve this. So the constant is not related, you can take it out, right? The constant is not related. You integrate with y square dy, right? We put together all the changes that related to y, and also you can integrate. You integrate your dx. Integrate your dx, right? So how much you need to integrate depends on your x and y, because over here in the questions they mentions your x is -3 to 3, then you integrate from -3 to 3, right? So you integrate from -3 to 3. On the other hand, also you can also integrate your dx also from -3 to 3 because it's the same. Okay, so after you integrate, eventually you can do it part by part, right? Dx, you integrate, you have x, then you have 3. So if I do it integrations part by part, yeah, 2 over here, right? -3, 3 y squared dy. So over here, I integrate x, 3 and -3, right? So over here is microcoulombs. This is uh, the unit, right? So I put it 3 minus 3, minus minus plus, so it becomes 6 over here. So 6 multiplied with 2, and then you continue to integrate y square dy. So y square dy, you integrate, you have y power of 3 divided by 3, right? And then you have 3 and -3. Okay, so unit is microcoulombs. We continue. So 12. So 3 power of 3 divided by 3 minus with -3 power of 3 divided by 3, right? Okay, so what you will have, so eventually I suppose you will have 18 multiplied by 12 microcoulombs. Okay, so after you press the calculator, I suppose you will have 216 microcoulombs. Okay, that's it for the total charge if I have this kind of the surface charge value. Okay. Boleh guys? Are you with me?
Yeah.
Right. Okay. Ada soalan tak? This is the example on the surface charge. Maybe we shall take a look at another one on the volume charge, right? Um, volume charge, yeah. Okay. So boleh kita move on to another example?
Boleh.
Or you need to take a break?
Sambung
tak?
boleh.
Take a break.
Oh, siap ada echo. Take a break. Okay. So kita take a break for 5 minutes saja, okay? Right. So kita stop for 5 minutes. Nanti kita sambung balik.
Baik, sir.
Okay. Right. Okay, guys, do let's continue on the second example on the continuous charge. So the first example, I show you um, the surface charge, right? Now let me show you a little bit on the volume charge. If you read properly the questions over here, a spherical cell centered at the original and extended to 2 centimeter. If the volume charge density given by 2 centimeter cube, um, find the total charge contained in the shell. Right. So these questions give you few informations over here. The first thing they mentions the shell is spherical. Right? This is the spherical shell, and it's actually located at the center of the origins as extended into 2 centimeter. Right. So this one is actually give you the radius, right? The radius. So if the volume charge density is represented by rho v, right? Given by uh, 2 coulombs per meter cube, right? So your rho v is 2 coulombs per meter cube, right? Um, so what else? Now you know that this one is actually the volume because it's given to you the volume charge density. But how do you know which volume, which formula to use? If you look at the formula over here, you have Cartesian coordinate, you have cylindrical coordinate, you have spherical coordinate. Now, I would like to ask you which one that you need to use, which formula. Uh, First of all, which part? Differential length, normal area, or volume? Which one? Yang mana satu yang patut pilih? DL, DS, or DV?
Volume. EV.
Okay, right. Volume. But volume, you have 3 formula. You have Cartesian, you have cylindrical, you have spherical. Which
Spherical.
one? Spherical. Why spherical?
Because it mentions spherical cell center.
Okay,
origin.
right. Because the problems mentions spherical. So we choose this one. We choose dv equals to r squared sine theta dr d theta d phi. Right? So from the formula you identify your dv is equal to r squared sine theta, right? And then 3 changes dr, d theta, and d phi. Why 3 changes? Because I told you before, in spherical coordinate system, you have 3 parameters. One is radius, one is theta, another one is phi. So when you want the volume change, when you want the volume of the spherical change, it should change 3 of them. All the 3 parameters change. dr, d theta, and d phi. All right? Now, the questions ask us to find Q, the total charge. And we know that Q, how do we find Q from the volume? If you look at the formula, you look at the formula, over here in electrostatic, you have 3Q over here. Q, you can find it out from rho LDL, you can find it out from rho SDS, or you can find it out from rho VdV. So it among these three formula, this one is actually matched with the informations provided from the problems. So I would use this one, the integrations of V and rho V and dV, right? Why do we use these? Because we have all these informations. We have rho V, we have dV, right? You see, then we can use this formula. So how do we use this formula? Since this one is the integrations with respect to the changes of the volume, right? dV. So what is the three, over here you have three changes, dr, d theta, d phi. So in this case, you replace everything inside. I would like to replace my rho v, which is 2, right? Of course, the unit is coulombs per meter cube, right? So if I write it out here, coulombs per meter cube, right? And then my dV, this is my rho v. My dV will be r squared sine theta dr d theta and d phi. Okay, what else? So in this case, it will be integrations. How many integrations involve? 3 integrations because involve dr, d theta, d phi. So we have triple integrations. So here, right? Okay, so let's move. When I want to integrate, I don't integrate those not non-related, right? So I take out the 2, which is the constant. You won't change anything. Over here, the volume, over here, the unit is meter cube, right? Meter cube. So in this case, the unit meter cube over here and the meter cube over here is automatically cancelled. Then you only have the coulombs, which is the unit for the charge. All right, now, then you can rearrange. You rearrange the formula. Rearrange the formula properly. Okay, so now I would like to integrate d phi, right? Do I have anything that related to d phi in this formula? No. So then I only integrate my phi from 0 to 2 pi. Why 2 pi? Because the questions mentions spherical. So if the questions mentions spherical, is not mentions half of the spherical, then you use 2 pi. If the questions mentions half of the spherical, then you integrate from 0 to pi, right? It depends on the shape of the object. Okay. Then what else? You next, you want to integrate after phi. You want to integrate theta, maybe theta. So those related to theta is actually the sine theta and d theta. Yeah, you cannot take out the sine theta as a constant because the theta will change according to the changes of the d theta. So your theta will have from 0 to pi. How I know my theta is 0 to pi? Because just now I mentioned to you in the coordinate system, in the spherical coordinate systems, the limit, if I shows you the textbook over here, right? In the coordinate systems over here, you already know that see your r is from 0 to 0 to infinity, your theta is from 0 to pi, your phi is from 0 to 2 pi, right? But this is for the complete spherical. So now, since our questions mentions nothing about the shape of the spherical, we assume the spherical shape is complete. That's why we integrate from 0 to pi. And then the last one, it's related to the radius from 0 to how many? Can I integrate up to infinity? Can or cannot? R square dr. Can I integrate from r equals to 0 to infinity? Because uh, in here, they wrote it from 0 to infinity. Can I? Boleh tak? Saya
Boleh.
integrate from 0.
So,
Boleh ke tak boleh? What we mean by infinity? Means your radius is infinity large, right? But in the questions, does the questions mentions the radius is infinity large?
no,
If you
it's
read
mentioned.
back, the radius is up to 2 centimeter only. So what you need to integrate, you integrate up to 2 centimeter, not to infinity. Right? So I integrate up to 2 centimeter over here. Right? Okay. Now, then I can integrate, do it one by one, part by part. Right? You can do it part by part. For phi is actually 2 pi and 0. Another one, negative, negative, negative. Because when you integrate sine, how much you will get? You will get cos. How do I know? Because this is the normal integrations, right? If you don't know, you refer back to the formula. The formula given, let's see the formula. Which page? Then you look for the integrations. Integrations. Where is the integrations? Okay, derivations and integrations. So infinite integral. So integrate sine. Where is integrate sine? Integrate sine. Over here, do we have? Yes, over here, integrate sine. Right? Then you have negative cos. You have negative cos. Right? So over here, you have negative cos theta, right? Because you integrate theta, then you replace pi and 0 over here. And the third one, r square, you integrate, you have r power of 3, right? And then you should replace 2 centimeter and 0. Okay, so the rest is just a normal mathematics. So 2 remain over here, 2 pi, minus 0 is still at 2 pi. And then negative 2 pi minus with negative cos 0. If you press the calculator, you will get 2. Okay, and then the last one is 2 centimeter power of 3 divided by 3. Okay, right, that's it. So eventually you should get 8 divided by 3. Okay, 8 times 10 power of negative 6. Okay, so eventually you should get 67.02 times 10 power of negative 6 coulombs. That is the total charge. Okay, so if we zoom in here, that is the whole solutions. Okay. Okay, so okay, it's already 10 o'clock. I guess we will stop here. So today, at least we cover from the mathematics revisions up to continuous charge. Yeah, right. So kita, I will stop here. So our second revision class will be on Sunday night at 8 o'clock. Any question, Syafiq?
Ada tu saya nak tanya.
Yeah.
Yang darat 2 pi darat 2 sebelah 2 pi tu mana dapat?
Oh, yang tu you replace masuk dalam ni. You replace masuk pi ni, negative cos pi tolak dengan negative cos 0. Nanti you akan dapat dulu. Boleh? Dapat? So yang ni tak ada apa pun, you just kalau you masuk negative cos pi tolak dengan tolak dengan negative cos 0, you akan dapat itulah 2 lah. Okay, right. So our second class on Sunday night, yeah, Sunday night 8 to 10, right? So second class kita akan cover on Gauss law, kita akan cover on electric potential, and then kita akan cover on the material space on boundary conditions a little bit, and also on the resistance capacitance a little bit, right? Boleh?
Boleh.
Yeah. So ambil masa, take your time to study this dari mathematics punya revision sampailah continuous charge dulu, and then you extend it a little bit in advance, study Gauss law, study electric potential sebelum kita masuk kelas on the Sunday night, right? And then another last one we will cover on Monday night. Kita akan cover magnetostatic, Maxwell equations, and wave propagations. Right, so I arrange in such a way so that you have some gaps to study and revisions, and you don't cram everything to study in one day, right? Electromagnetic, you cannot study last minute in one day. You very stressed because you need sometimes to digest, to understand. Okay, so I don't want to talk much. We will stop here. I will see you on Sunday night, 8 o'clock sharp. Okay, right. Thank you very much.
Okay.
Kalau ada soalan,
Thank
boleh
you,
PM
sir.
tepi. Kalau malu-malu nak tanya, boleh tanya dalam group ataupun PM tepi lah. Okay.
Well,